All right, so the final type of solution that we're going to learn to calculate the pH is for salts. We actually already have all of the skills we need to calculate the pH of salts because we've already learned how to identify whether salts are acidic or basic by looking at the ions making up the salts. And once we've identified which ion or ions are going to have an impact on the pH, that ion, however we would calculate its pH, is what's going to be used to determine the pH of your salt. So if they're neutral salts, their pH is going to be 7. If they are a strong acid, you already know how to take care of it. If it's a strong base, you already know how to take care of it. However, if the ion making up the salt is weakly acidic or weakly basic, we'll have to use our Ka expressions to calculate pH. So I've got two examples for you. 0.40 molar NH4ClO4 and 0.45 molar NaOCl. So we're going to take one of them at a time. If we look at NH4ClO4, we know that that cation is coming from a weak base, so that is going to be weakly acidic. And then the ClO4 minus is coming from a strong acid, so that's not going to have an impact on my pH. So if ammonium is going to cause a solution to be acidic, if I add it to water, I should be able to produce hydrogen ions. With NaOCl, the sodium, that alkali metal, is not going to have any impact on my pH because it's coming from a strong base, but the OCl minus is coming from HOCl, which is a weak acid, so this particular salt would be basic. If I start with NH4ClO4 and I write an equation showing how NH4 plus can combine with water to produce hydrogen ions, it's acting as an acid, it's going to donate its proton, that would leave me with NH3 and the hydronium ions. I have my Ka value I can get from my chart, 5.6 times 10 to the negative 10th. This is the first time you're seeing me not set up an ice chart because, as we've seen in those previous problems with weak acids and weak bases, you don't have any of the products, you only have the reactant. Look at that concentration of NH4 plus. It's the same as NH4ClO4, and it's 0.40 molar, which is substantially larger than 5.6 times 10 to the negative 10th. If I go through and solve for x by assuming the change in ammonium would be negligible, I get an x of 1.5 times 10 to the negative 5th. I feel quite confident in saying that that's going to fall well below the 5% rule, but that x is giving me my hydrogen concentration. So if I take the negative log of that hydrogen concentration, I get that my pH will be 4.82. If I look at NaOCl, and I focus on the OCl minus ion, we know that when that is added to water, it cannot donate protons. Again, this is going to be a basic salt. It has to accept a proton, and it's going to produce HOCl and hydroxide ions, which is how we calculate POH. I can set up a similar K expression as I did with NH4ClO4, but this time I want to use the Kb value for OCl minus. 2.86 times 10 to the negative 7th. This is even not as small as the previous one, but is still significantly smaller as a K value compared to that initial concentration. So if I go through and solve for x, I get that it would be 3.6 times 10 to the negative 4th. That's my hydroxide concentration. So if I take the negative log of that value, I get that the POH would be 3.44 and that my pH would be basic. Again, just providing additional or quantitative support that you can have acidic salts with NH4ClO4 and basic salts with NaOCl based on the types of ions that are making up those salts if they have weakly acidic or weakly basic components.